In this lecture, then, what we want to do is we want to extend the concept of differentiability at a point to just extend it. So, in a couple of ways. So, let's explore that idea. I'm just reviewing the information we had from the last um, lectures. Uh, the slope of the tangent line, right? A function is differentiable if we can obtain a slope of the tangent line. And that's the limit of the secant slope function. In fact, this definition is most useful when the function is piecewise, as we saw in the examples in the last time. Then you really have to use this. Notice that when we write x equals a, we really mean a point, right? This is a function. So from the very first lecture, by definition, when I tell you the x value, you have to tell me the y value. And that y value is in the notation of functions f of a. Okay, so we really have a point. When we say x equals a, we have a point, and then dy dx is the slope. So if a function is differentiable, I have a tangent line, I have a linear approximation. And again, you're going to see this is key to really what calculus is all about. Now, what we want to do, among other things, is extend the definition of differentiability from a point to an interval. And we'll do this exactly the same way we did it with continuity. We'll say a function is differentiable on an interval, provided it's differentiable at each value of a, x equals a, for all a in the interval. And we write f is an element of the set of differentiable functions. And it'll be d1 because it's first derivative. Okay, so just as we used C for continuity, we're going to use D for differentiability. Okay. Now, this is the issue. So here's x cubed. That's just a prototype of a polynomial, right? A polynomial. And let's evaluate this instead of at a fixed number. Let's evaluate it at a. This is a parameter at the top of the code that we'll fix, right? It can be anything we want, but we have to fix it. Now let's go through exactly the calculations before. Okay, so I'm not going to specify. A could be 1, a could be 1/2, it could be any ridiculous number I want to come up with, right? It can be anything. And the steps are going to be exactly the same, only we're going to have this placeholder in there. So f of a exists, it's equal to a cubed. Remember, a is a number. I don't know what it is, but you have to fix it. We can compute the secant slope function, right? We're just going to substitute in the rule. And again, keep in mind, f of a is in fact a number. So the function rule, f of x is x cubed. F of a is in fact a cubed. And what we're looking for is in the bottom, x minus a. And we've done an example like this. The trick here is this is the difference of cubes. And so there's a formula, and we can cancel that out. And the reason we're going to need that is we're going to need an extension, right? The secant slope function is never defined at a. So here's a summary of what we have, and I want to evaluate the limit. Again, these slides are a little more sloppier than the ones marked problems because I did these first and then, I developed it. But anyhow, we need the extent. We develop an extension. I need the extension theorem. I mean, keep in mind, a is a fixed number. So this is x squared plus a. A is a fixed number, ax plus a squared. That's just a number. A is a number, right? Keep in mind, it's like 2, whatever. It's just a number. So by the extension theorem, these two both have the same limit, and it's continuous. It's just a polynomial, and we can evaluate its limit just by plugging in. Okay, and we get 3a squared. And so you see there's a pattern here. The slope of the tangent line when x equals a is 3a squared. So let's examine this. This is going to play a role throughout the course again. When x is 3/2, when a is 3/2 is what I'm saying here, right? When x is at the value of 3/2, that says a is 3/2. The slope of the tangent line is in fact 6 3/4. You can see the picture of the tangent line here, and that's the point. That's your tangent line, would be your linear approximation. So when I fix x to be a's 3/2, the slope of my tangent line is 6 3/4. So I get a slope, and I get a tangent line, and I get a linear approximation, all by saying that a is 3/2. If I take a to be 1, when x is 1, x is a is 1, the slope is 3. And I have a point, and I have a slope, so I also have a tangent line and a linear approximation. So when x equals 1, I get a slope and a linear approximation, let's say. When I choose a to be 1/2, right, same thing. Same exact thing, right? I have a slope of 3/4. When a is 0, x equals 0, the slope, the point is 0, 0. The slope is 0. I have a linear approximation, and so on and so forth. So when every time I specify a, and x equals a value, I get a slope and I get a tangent line. Which, again, you can begin to see how we're going to approach this, right? Look at the picture. What are we going to actually be working to do? We're going to be working ultimately, fundamental theorem of calculus, with replacing the function by its piecewise linear approximations. Do you see how that's going to work? I mean, you can start to get a feel for what we're trying to do with calculus and why it is, in fact, so powerful. But back to the original point here. For any x value, right, any x value, I can associate with that x value a number, a slope, or in fact a linear approximation. Okay? And this is the function that associates that value, right? That value of the slope. So if you say a is 3/2, the slope is 6 3/4 of the tangent line to f. If I say x is 1, the slope is 3 of the tangent line to the function, not this, to the function, to the original function f. And all the way around. So I generated another function, right? And this function derives from the function f. You see where I'm going with that, right? It's the derivative. This function, constructed in this manner, derives from the function f. Why is that important? The function f gives you the point. This function gives you its slope. A point and a slope gives me my linear approximation. Okay? And that's what's important about this. I have all the data I need between the function f and the function g to construct a linear approximation to the original function. All right? So that's it. Now, I'm putting both pictures on the same, both graphs on the same slide here. And we can see the connection here. So if I pick x equals 3/2, that is a was 3/2. The slope of this tangent line is, well, 6 3/4. That's what I get from looking at this graph G. Right? That's how I construct this graph. So the graph G contains the slope information for these tangent lines here. Right? So this function g is constructed by determining the slopes, and on the other end, it tells me the slopes if I have this function g. So again, these two graphs are intimately related, right? And the one g is derived from the function f. It tells you the slope of the tangent lines. All right. Now, so again, let's think about this in another way. And again, now we're starting to get into more advanced ideas and the real ideas of what the domain and the range mean. So another way to look at that is, if I have a function f, by using this construction technique, I have a new function g. Now you're used to saying functions are like f of x equals x squared. So I tell you 2, you say 2 squared is 4. That's not what we're doing now. Now I'm telling you there's a function. I'm telling you the input is this function f, and you're telling me the output is this function g. So the relation that this is a function. The input is not a number. Notice the domain here. It's going to be differentiable functions, functions who have a derivative at every point, right? Because that's how I generated g. And the range is going to be, okay, we need to be more technical, but essentially let's say functions. So a function that's differentiable goes on the inside, goes on the in, and I get a function on the out. So there is a function. This is a function that takes functions in and spits functions out. So I'm not going to call it little f. I've already used that. So let's call it capital F. Right? So there is such a function. Right? Again, the inputs have to be differentiable, right? Because for each point, I need a slope of a tangent line, right? And that's what we get if we're differentiable. Okay. Now, this is just notation. The function g, again, I don't want to call it g. I can't call everything f. I can't call everything g. G is derived from the function f, right? So I need a terminology for it. I'm going to use fx. Now, since we only have one variable, and people like to use the tick notation, and I really don't like it. I mean, for me, at my level, I get it. But I mean, even though it's a function of a single variable, this variable changes. The variable could be x. If we do composition of functions, it's going to be x and y. So the variable, it is true that each function has only a single variable in Calc 1. Calc 3, you do multivariable. The variable is not the same, right? They're not the same variable, and it's important to keep track of this. The chain rule is based on composition of functions. So for the chain rule, I need to keep track of the variables if I'm going to do it efficiently. Substitution, integration by substitution, is the antiderivative form of the chain rule, and once again, I need to keep track of the variables. So I don't find it useful to write f prime. If you want to do it, knock yourself out, but I don't find it useful. And this is the notation that I'm going to use. Also, when you go to multivariable calculus, calculus 3, you can't tick. Your variables might be x, y, z in time. So you can tick. You're going to be using this notation again in calculus 3. So again, this isn't unique to me. This is standard notation, but I'm going to use it here as opposed to maybe the more common tick notation, which I just don't see any advantage to that in this context. Okay, so let's go on. This function f, just in terms of terminology, it is a function. It takes the function f into the function g, or the function f into the function fx. We call those functions of functions operators. So that'll be an operator. An operator is a function. It's just that the input isn't a number. It's a function. So again, if you have calculus, sine goes to cosine, right? Or x squared goes to 2x. That's an operator. A function goes in, a function goes out. Okay, so it's an operator. Now, let's look at it. We have to name this operator, this function. What am I going to call it? I can call it anything I want. Anything I want. So what kind of special name am I going to pick? Again, the notation should make sense. So this is where it comes from. I'm going to call it d over dx. The d doesn't stand by itself. The dx does. It's one chunk of a notation. So instead of, see, this is the function notation. F of x goes in, right? Instead of 2, instead of the number 2, and 4 comes out. F of x goes in, and g comes out. Okay, what I'm going to call the function now is d dx, and I'll explain why I picked this notation. I mean, you could call it anything you want. Why not call it something that helps you understand what it does? And the output, because it's derived from f, right? At each x equals a value, you have to tell me what that number is. It's the slope of the tangent line. So the function g is derived from f in a very specific way. I'm going to call it fx. See, x is the variable. And if I had multivariable calculus, again, it goes through. If the variable was y, I'd call it fy. So everything is x. Now let me explain why we picked this notation. Okay, this huge box is just a summary of what I had. Because the output function is fx. Now evaluate fx at any value, at any point, right? At any point. So a is a fixed number at any point. And what does it give you? How did we construct fx? By definition of the construction, go back and look. At each point, at x equals 1, for example, it was the slope of the tangent line, the function f, at x equals 1 in the y value at that point. The slope of the tangent line. And the slope of that tangent line is dy dx. Now notice what I'm saying. It's just a function. Fx in and of itself, it's just a function. But its interpretation, if you put a number in here, an actual number, not an x, an actual number in there, the number that comes out is the slope of the tangent line of the function f at this point, right? That's what it says. It's a slope, change in y, change in x. So I'm just going to piggyback on that. See, I'm just going to take the ddx here and plug it up here. See, this is a y. Right? Y equals f of x. So that's where it comes from. That's how it's implied. And again, there are brackets. There should always be brackets here. Because again, it's a function, right? A function of f. F goes on the inside. I mean, you wouldn't write f of x equals x squared as fx equals x squared. You put brackets in. We should be using brackets here. This is a function. This is an operator, in fact. It takes a function in, not a number, a function in, and gives me a function out. That's what this does. And so why call it this? Because I'm trying to remind you that this is related to the slope of the tangent line. The function that comes out of this, it converts this function into slope of tangent lines. So, I mean, again, I think it's a pretty good idea. I mean, again, if you can come up with a better idea, do so. I mean, the notation has to make sense, right? It's not random. If you can come up with a better idea, I mean, good for you. I mean, let me hear it. Okay, so this is it, right? But it's only a slope if you evaluate it at a particular number. If otherwise, it's just a function. If it's fx and that was an x here, this is just a function. But at a particular value, it gives you the slope of the tangent line of this function. Okay? And again, I'm just saying you have to pair up the variables, and you'll see how this comes in both when we do chain rule, when we do substitution, integration by substitution, and in particular when you do multivariable calculus. This is essential. So my variables have to pair up, right? Everything has to pair up. If this is x is the variable, and so forth and so on down the line. And again, you'll see why this plays out. I mean, the chain rule might make more sense to you if you keep track of these things. Okay, so we'll work on that later. So again, let me explain this again. My operator is ddx. This is the notation. This also means this. It says a function goes in and a function goes out. Right? They're just purely functions. Of course, they're related, and fx is derived from the function f. Okay? So we can look at this function and this operator in a number of ways. So for an arbitrary but fixed point, you have to tell me what a is. It's a parameter at the top of the code. You have to set its value. It could be 1, it could be minus 1/2, whatever. If you evaluate this function, this operator, then a goes in, right, fx, a goes in, and the slope of the tangent line comes out. So that's what this function fx tells us. The function derived from fx, it'll be the derivative, right? We're going to call it the derivative. An x value goes in, a number goes in, and the slope of the tangent line comes out. Right? That's what this function is. It's just a function, but when we plug in a number, it has an interpretation. Notice when you say f of x equals x squared, you plug in 2, you get 4. There's no interpretation. 4 is just 4. But the output here, I could plug 2 in, and the output here would be the slope of the tangent line. Of course, it's just a number, but it's the slope of the tangent line. Okay? So notice, this is why domain and range is really important. Okay? I mean, up till now, so for some implicit functions, it had its uses. But I'm going to say, I have to write a function. I need a rule, which I've specified here, but I need to set x and y. Notice the domain is a number. What goes in is a number. And if the range comes out, it's a number. That number is the slope of the tangent line. So you say nothing new there. Okay, good. Right there, that's it. But notice, this is the point. I not only get the slope of the tangent line, I can get the linear approximation, right? Which is really what I'm interested in. Remember that picture. I replaced that curve, essentially, by its linear approximation pieces all over the place, right? So in that case, if I take a linear approximation to associate with each number, then notice what this thing generates, this fx. So the number goes in, but the linear approximation comes out. right? The linear approximation comes out. So a number goes in and a function comes out. So here, the domain is the real numbers, but what comes out are actually linear approximations. It all depends on how I set my range. Remember, I told you the range is usually, am I talking about real numbers, complex numbers, differentiable functions? That's what's happening here. The same function, but if I set, well, the same rule, but if I set the output to be real value functions, well, now it's different. A number goes in and the linear approximation comes out. So that's kind of interesting how you can interpret this function, fx, the derivative. So let's move on. Again, that's not testable, that's just for your own interpretation. So let's look at this. How should you think about it? A function goes in, this is an operator, and a function goes out, and I can also write it like this. So this function derives from this function. Right? And so that's it. And we should think of, so that's as a function, but at a specific number, what we get is, through the derivative, we either can interpret it as giving us the slope of the tangent line, right? Either it's giving us the slope of the tangent line, so a number goes into this function, and the slope of the tangent line comes out, or you can interpret it more directly as a number goes in, and the linear approximation comes out. So, I mean, it's pretty interesting. I mean, you really have a lot going on here. So, again, in a functional sense, the function f goes in, the function fx comes out. They're just functions. But at a particular number, the output function tells us the slope of the tangent line, or really the linear approximation, depending on how you specify the range. So you get a lot of information here. Again, this is kind of the advanced idea. Okay, here's my picture. So notice, everything is always of this form, right? d dx, that's the operator. F goes in, fx comes out. So when I write d dx x cubed equals 3x squared, what am I really saying? I'm saying the function that goes in is x cubed, and I'm saying the function that comes out is 3x squared. And here's the picture. Here's the function f, here's the operator, and here's the function, the fx that comes out. So this function gets mapped into this function via this operator. And that's how we interpret this formula. So again, here's a particular example. And we want the slope of the tangent line at this specific number at a point. Okay? Now we could do this using the definition of the derivative at this point. We could do it like the last section. But let's go a little high speed now. This function is differentiable. So we'll use differentiation on the interval. Yeah, I mean, that's just the key, right? It has to be differentiable. We're not talking about a point. You have to be differentiable to the left and the right. So let's do it. Determine f of x on the interval, right? So we know that the derivative of x squared, we did this one example previously, derivative of x squared gives us 3x squared, right? Put any a. The derivative of this function is 3x squared. So this tells us the input function is fx and the f of x, and the output function is the derivative fx of x, 3x squared. But at a point, so determine the slope of the tangent line, by definition, that's how this function was derived. By definition, at a number, put in the number here, this gives you the slope of the tangent line. And this is 3x squared, so it's 12. And that's what we got before. So it's slick. I mean, it's a lot easier to do it if you have this function available. And we can determine formulas like this for a few simple cases. Okay, and that's what you know as the differentiation rules. Okay. So let's come up with some other things we know. We know if a function is differentiable at a point, at a number, right? At a number or at a point, it's continuous. And we say it's differentiable, a function is differentiable on an interval if it's differentiable at all values in that interval, at all x values in that interval. So combine these two and we say if it's differentiable, if a function is differentiable on that interval, then it's continuous on an interval. Again, it's a regularity result. The air temperature, pressure, and whatever density of the room is differentiable. Actually, it's more than that. But it's continuous, but it's also differentiable more so. It's smoother than just continuity. Okay? What types of functions are differentiable on intervals? Well, you'll see. We'll see the formulas. Essentially, polynomials, rational functions, where they're defined, trig, exponential, logarithmic functions, where they're defined, where everything's defined. The usual suspects. And you'll see, we'll have differentiation rules for that. So what good is differentiability? I mean, that's a good question. Right? Well, let's come back and look at this. Now, we haven't finished this yet. We'll be using global optimization on closed and bounded intervals. We'll be poking at this throughout most of the semester. But what we left before is if I only add continuity, remember, including the endpoints, I can just tell you there's a maximum minimum value. Right? So if you talk about the temperature distribution in the room, it's continuity up and including the walls. I can tell you there exists a maximum temperature and a minimum temperature. I don't know where, right? I don't know where. But I told you then, if you give me more smoothness, I can give you a better answer, right? So a number is a zero provided that the function value equals 0. So let's see what I can do. I can complete that. In fact, I can phrase this a little better, and we'll do that later. If I say that the function is continuous on the closed and bounded interval, so the air temperature, whatever, is continuous up to and including the wall, but it's actually differentiable inside, right? That's a smoothness statement, right? That's a smoothness statement. Then the extremum, which means maximum, minimum, global, over the whole room, right? And everywhere, not just local, global, everywhere. The global extremum occurs at either, and I can't tell you exactly, but I can narrow it down, at the endpoints, right, on the wall, right, at the endpoints on the wall, right, that's the left side, that's the right side, we're one-dimensional result here, or at a 0 of the derivative. I can tell you where it is. I can't tell you, it can be one of a few values, but you just make a table and compare. So that's pretty good. Why is this result so important? Optimization comes up all the time. And even when you don't have a closed and bounded interval, and in the actual lecture when I'm in the class, I talk about it, you use this all the time. This is really the big result. I mean, even when it doesn't apply, you do things to make it apply, right? And again, in the lecture, I talk, in the actual class, I talk a lot about this. So it's a big result. I mean, this is probably the biggest result of differential calculus, this global optimization theorem, in my opinion, okay? And notice, you can just keep milking this. I mean, if you're looking for a 0, that's the intermediate value property tells you that you have a 0. So if you put a little more regularity and say then that the derivative is not only differentiable, but the derivative itself is continuous, you can use the intermediate value property to find the zeros, etc., etc., etc. You'll see if you have a numerical methods class, you'll have results that say these things. If your functions meet these conditions, here's an algorithm, you can find these results. I'm not going to make a big deal out of it. I'm just trying to point out that these things are there. Smoothness is an issue. So these are the rules you can come up with. If you just apply the definition of the derivative, and I think in book derives that you can find them. I'm not going to, like I said, I'm only interested in deriving things like the fundamental theorem of calculus when it's useful, when you gain insight. These are just rules. Remember, d dx is an operator, it's a function. I'm saying that this function goes in, and if this function goes in, I can take out the constant. That's how the operator works. If I have a function composed of two functions, right, that you're adding together, you can break them down. Notice everything here is divide and conquer, right? Now, I like writing the quotient rule like this because, again, I think it helps make the problem modular. You'll see when I work out the problems, especially when you get the chain rule problems and so forth and so on. Notice what I'm always doing. I'm taking a complicated function and I'm breaking it down into the two constituent parts, the two constituent pieces, right? The derivative here and here. I probably should have wrote this term first. I know it's all f and g's, but it's fudge factor, first one, fudge factor second. They're all the two pieces. And again, when the problems are complicated, I'll just break these off, work them out on the side of the page, plug it back in. And that's why I kind of prefer this approach. But if you have the quotient rule from high school and you want to do that, whatever. I mean, whatever. I just think it's better when you can break things down. You see, everything breaks down into two. Okay, that's the idea. So these are the rules. Specifically for, remember I said you can derive these rules for specific type functions. Powers, right? Powers, it works, right? Now again, r has to be a constant here, so keep that in mind. Now again, what's your function here? Be clear on this. Your function is x squared, x cubed, x to the 1/2, x to the -2. It has to be x. This is your function, right? This is fx. This is f of x. This is fx of x, right? So it has to be exactly x to some fixed power. Sine of x. It's not sine of x plus 5. It's sine of x. Sine of x, the derivative is cosine. And again, cosine is minus sine. So these are the only ones we're going to concentrate on now. These are the building blocks. We'll add to this later. So here's an example. Here's an example. And I want you to find the tangent line, the slope of the tangent line when x equals 1, or at the point 1, f of 1. So let's go through it. Now in the next lecture, we're just going to work these out. In the lab, we're just going to work these out. It's always a good idea. It's always a good idea to simplify first. You don't have to, but I mean, it's like walking and texting. You're going to walk into somebody. Now, okay, r plus, you don't need this. It's just this is only valid for x that are greater than 0, right? Because you don't want the bottom here to be 0. Now, this isn't in the right form, right? This is what you have. We don't have a sine. We don't have a cosine. We want things that look like x to a power. This is not x to a power. So I want to simplify and put this in the correct form. Look for it. It'll make life easier. So I'm just going to do it over here. And again, I listed my crib sheet rules. I said. So square root of x is x to the 1/2. And that's what the rule means. It's x to the 1/2. I'm just taking my time through here. If you have cubed root of x squared, right? The cube root is to the 1/3 power. X, well, it's this rule. So this is x to the 2/3 power. But I still don't want it in the bottom. I want to write it like this. Okay, I want to bring it up to the top. And again, if you're fuzzy with these rules, we just need to practice. Right? So this is the form that's most useful for applying the rules. Notice what I have. Constant times x to the power plus constant 1, x to the power. You can have constant sine, constant cosine. Those are your building block functions at this point. Everything you do should look like that. Okay? I know since this function is differentiable, it's powers, I can apply the differentiation rules. So how am I going to do it? I'm always going to just calculate. I do this better actually in the problem sets on the next day, but let's just go through it. There's only one rule that will apply at this level. Look at the list I gave you. Only one rule can work. Again, it's not fate versus free will. You're the technician. You're the machine. This is why you can code this stuff. Derivative calculators. There's only one rule that can apply here. Look at the sheet. Which one is it? I mean, by the process of elimination, it's only the sum rule. Right? I identify the functions here. It's the sum rule. You have one function here plus another function there. The only rule that can apply is the sum rule. It has to fit exactly. I mean, if you're going to use the rule, you have to tell me what the pieces are. You don't have to write it down, really, but you know, that's the idea. Now, I've broken one problem down into two problems. So what rule applies here? Which rule? There's only one. Only one rule can apply on this piece. Only one rule. Okay, try and find it. Constant rule, right? I mean, you literally have to tell me what you're doing. The constant is a 2, and the function I'm referring to in the rule is the 1/2, x to the 1/2. It's the only rule that applies. Learn to play the game, and it'll be very efficient. Okay? Now, if I look at this term, or this term, either one, there's only one rule that can apply, right? Take a second and look. It's the power rule. And in particular, this power r is 1/2. You just cut and paste. If I look at this one, what do I have? Same, r is minus 2/3. It's just a matter of doing the algebra. And I'm just putting it all in here to show you can simplify, right? I'm just putting it all in here to show you. Yeah. Now, what was the point of this? Okay, at the end of the day, this function came out. So it was the one function went in, and this is fx. Why did I put all those steps in there? Because I want to show you. You get into the habit of skipping steps, taking shortcuts. I am not against you doing that. You know, it's a pro and con argument. The argument for skipping steps, if you don't, it'll take 10 pages and you'll die of boredom before you get to the answer. What's the negative? The more steps you skip, the higher the probability that you're going to make a mistake. So you need to have a balance, right? You need to have a balance. If you're skipping a lot of steps, I mean, to grade it, that's fine. But the negative is you're more likely to make a mistake. You have to find a balance that you're comfortable with, right? Otherwise, it's not good. But if you were to code it, you'd put in all the steps. I mean, if you look at how the derivative calculators or algebraic simplifiers do it, you can have them all list out every single step, and you'll see. But usually, you don't want to see that. But I'm just saying, I'm not against you not putting in the steps. You just have to know what the golden rule is, right? What's a good trade-off between shortness and making an algebra mistake. So once I have this function, the derivative function, the function derived from f, I can find the slope of the tangent line for the function f just by plugging in. X is 1. So you plug in, and you get the slope is 1/3. And then this is how you do it. If I have the slope of the tangent line and a point, I can come up with the linear approximation. So it's just, this is a way, well, for some basic easy functions, easy quote, in quotes, for a basic family of functions, basically, essentially powers, polynomials, sine, cosine, we'll have others. But it's not unlimited. It's a very finite source of functions. You have these rules. The key is, if the function is not piecewise, this is probably an easier way to go than using the definition. Okay? So again, I just want to emphasize the difficulty with skipping a lot of steps is that it just leads to mistakes. So just be cautious. Now here's another example. Oh, this was the example we had. So find the tangent line. And this is going to work exactly the way we did. What's your data? Y equals mx plus b. So again, pause and give it a try. Okay, here it is. We have, I prefer, I mean, the way I did it in the problem section is better, but I have a point and I have a slope. Again, I have the point, I have the slope, and then it's y equals mx plus b. Substitute in the slope, substitute in your data, solve for b, and you're done. And again, you can also do the linear approximation. And it's actually a function. I should have a domain and range. So these are the standard kinds of calculations. And we're going to practice this technique. And I want you to get comfortable using the rules. So next lecture, we're just going to work out problems. And in the lab, you're just going to work out problems. And then hopefully go home, try a few, and you should be a pro. Okay, so good luck with that.